Welcome to Full Spectrum Science Shorts. I'm your host, Ron Hipschman. One day, in the not-so-near future, there will be no more total solar eclipses visible from the Earth. In this Shorts, we'll explore what's causing this and when this will occur in this program called The Last Eclipse. Surprisingly, the reason total solar eclipses are doomed is because of the actions of the tides. Let's review the effects of the moon's gravity on the waters of the Earth. If we consider only the moon for now, its effect is to stretch the oceans, creating two high tides, one pointing at the moon and one pointing away from the moon, and two low tides at right angles to these. The moon isn't the only actor on our stage, though. We also need to consider the sun. Although the gravity of the sun is much stronger, in fact, about 176 times stronger, what's important in creating tides is the difference in the pull from one side of the Earth to the other side. Gravity gets weaker with distance. Because the moon is so much closer than the sun, the difference in the moon's pull between the near and far sides of the Earth is much greater than the difference of the sun's pull. If you do the calculations, the moon's pull falls by 7% from one side of the Earth to the other, while the sun's pull falls off by only 3.2%. This results in solar tides being less than half as high as lunar tides, like you see here. Of course, we must consider both lunar and solar tides together. As passengers on the rotating Earth, we're carried through the high and low tides. If you observe the little person in our diagram, as she's standing on the rotating Earth, the rotation carries her through low and high tides. Sometimes her head is above the water, and sometimes she's below the surface. Most places on Earth experience two high tides and two low tides every day, though there are exceptions. Generally speaking, the tidal bulge follows the moon. From new moon to the next new moon takes 29.5 days, so the Earth rotates 29.5 times within the tidal bulge as the moon orbits around the Earth. Note that the Earth is rotating much faster than the tidal bulge. The relatively fast rotation of the Earth and friction between the Earth and water drags the tidal bulges slightly ahead of the moon. The white arrow is pointing out where the high tide bulge points. Note that it's always leading the moon. This means that the forces acting between the Earth and the moon aren't quite balanced. Remember Newton's third law? For every action, there's an equal and opposite reaction. So, if the moon pulls on the waters of the Earth pull on the moon. But with the bulge being dragged ahead of the moon, we have to consider not only the force of the water pulling the moon towards the Earth, the red arrow, but also the fact that the bulge is in front of the moon, pulling the moon forward, the yellow arrow. This pull will accelerate the moon, increasing its speed. This has consequences. As the moon moves faster in its orbit, it spirals away from the Earth. Whenever you add velocity to an orbiting object, whether it's a satellite or the moon, you change its orbit, moving it farther from its parent body. By the way, as this happens, the Earth slows down as the moon speeds up, making the day longer. The effect of the orbit change moves the moon farther away. The further away the moon, the smaller it looks in the sky. The moon's moving farther away isn't happening very fast. In fact, the moon moves only 3.8 centimeters from the Earth every year, about the size of a ping pong ball. We can already see these effects without waiting for the moon to slowly move away. The moon's orbit is not a circle. It's an ellipse. As the moon orbits, it's sometimes farther from the Earth, called apogee, and then about 2 weeks later, it's closer to the Earth at perigee. The moon is 45,000 kilometers closer at perigee than at apogee. That's almost a 12% difference in distance and hence in size. So in the course of 1 month, the moon grows and shrinks. Here, you see the biggest and smallest the moon gets. Let's split the moons and shove them together to make the comparison easier. As you can see, there's quite a difference between perigee and apogee. 12% difference. Likewise, the Earth's orbit is also an ellipse. As it orbits, it's sometimes farther from the Sun, called aphelion, and then about 6 months later, it's closer to the Sun at perihelion. The Sun is 5 million kilometers closer at perihelion than at aphelion. Like the moon, in the course of 1 year, the Sun grows and shrinks because of the Earth's elliptical orbit. Here, you see actual photos of the Sun at the biggest and smallest in the sky. Again, let's split the suns and shove them together to make the comparison easier. There's less difference than the moon, only 3.3% with the Sun, because our distance from the Sun doesn't change as much percentage-wise. This is a good thing, since we really don't want wide temperature swings on Earth between its close approach at perihelion and its furthest distance at aphelion. Now, what does this all have to do with solar eclipses? At this point in Earth's history, the apparent size of the moon in the Earth's sky is almost exactly the same as the Sun. This means that at certain times of the year, when all three are in alignment, the moon can just barely cover the Sun with only a little to spare. But even today, when the moon is near apogee, farther from the Earth, it looks smaller in the sky. Also, when the Earth is near perihelion, so the Sun looks larger, you won't get a total solar eclipse. The moon won't be able to completely cover the Sun, and we'd see an annular eclipse. The word annular comes from the Latin word annularis, or ring-shaped. To eliminate total solar eclipses, the moon at its largest should not be able to cover the Sun at its smallest, leaving us with only annular eclipses. To make this happen, the moon must be 21,400 kilometers further away. At that distance, the moon will no longer be able to cover the Sun under any circumstance. At the moon's recession rate of 3.8 centimeters per year, how long should this take? Okay, don't panic. A little simple arithmetic can solve this problem. First, we'll convert kilometers into centimeters, since we need to be using the same units throughout. There are 100 centimeters per meter and 1,000 meters per kilometer. So, there are 100,000 centimeters in 1 kilometer. We need to multiply our 21,400 kilometers by 100,000 to convert to centimeters. That gives us 2,140,000,000 centimeters as the distance the moon must move away from the Earth. The chalkboard's getting a bit crowded. Let's erase most of the numbers. Now, we only need to divide our distance by the 3.8 centimeters per year speed of the moon's recession to get the answer. In about 563 million years, it will be impossible for us to experience a total solar eclipse from the surface of the Earth. And this is all because of the tides. So the lesson here is that you should go and experience a total solar eclipse while you still can. In a little more than 500 million years, you will have missed your chance. Put it in your calendar. Thank you for viewing Full Spectrum Science Shorts, presented by the Exploratorium in San Francisco. This program, like all Exploratorium programs, is only possible because of donors like you. We know that this time is challenging, but if you can, help us keep educational content like this free and accessible to all by donating today at www.exploratorium.edu/connect. Thank you.